Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is Tangents to Polar Curves. As always, please be an attentive learner while watching these videos. We now need to discuss some calculus topics in terms of polar coordinates. We will start by finding tangent lines to polar curves. In this case, we're going to assume that the equation is in the form r equal f of theta. It's awfully easy to roll over this, but this is actually a huge assumption. You see, r won't always be a function of f of theta, and even when it is, it won't be easy necessarily to put it into this form. So this is a huge assumption that r equals f of theta. Having said that, with the equation in this form, we can actually use the equation for the derivative dy dx we derived previously when we were talking about parametric curves, and the chapter was called something like Tangent Lines with Parametric Equations. To do this, however, requires us to come up with a set of parametric equations to represent the curve. Now, this is actually pretty easy to do, but the reason it's easy is because of this assumption that r is equal to f of theta. This is a big deal. Okay. From our work in the previous section, an earlier section, we have the following set of conversion equations for going from polar coordinates to Cartesian coordinates. X is equal to r cosine theta, and y is equal to r sine theta. Now we're going to use these facts because you see you've got an r there and an r there, but now we're assuming that r is equal to f of theta. So we can substitute r equal f of theta into these equations, and we can say now x is equal to f of theta times cosine of theta, and y is equal to f of theta times sine of theta. You see, theta is now a parameter. It's just like t before. So what we're going to do is we're going to use our equation before that we had from this section, tangent lines with parametric equations, but now the parameter is theta. This is pretty slick and has everything to do with this assumption. Okay, so now we have this and this. Now notice that x then is not, it is a function of theta, but it is a product. You're taking f of theta times cosine of theta and f of theta times sine of theta. So this is going to be the product rule when we take the derivative. So what we're going to do then is we're going to take the derivative with respect to theta of this one. Now that's the product rule. So it's the derivative of the first, f prime of theta, times cosine of theta, and then it is f of theta times the derivative of cosine theta, which is minus sine of theta. So this is what we get for dx d theta. dy d theta is equal to, again, it's a product, so it's the derivative of the first times the second plus the first times the derivative of the second. And another way to write f prime of theta is, because we said that r was f of theta, is dr d theta, and dr d theta here. So you see we have these two things are the equations. But from before, we knew that to get the derivative with respect to x when we had parametric equations with theta as the parameter, we can go dy d theta divided by dx d theta, assuming this isn't equal to 0. So the derivative dy dx is then this. So you see, this is a new formula for you. It says the derivative with respect to polar coordinates dy dx is equal to dr d theta times sine of theta plus r cosine of theta, all divided by dr d theta cosine theta minus r sine of theta. Please make note of this. We'll be using this in our examples that are upcoming. And here's the first example. So determine the equation of the tangent line to, this is r equal 3 plus 8 sine theta at the point theta equal pi over 6. Now there's a lot involved in this equation. We're given a polar equation, so we have to know what is that. This is what the value of theta is. And although some people would say it's clear from the context, I think maybe I should mention that this tangent line, we want to have this tangent line in the form of y equals mx plus b. not in a polar form. So anyway, you know what to do. There's benefit in giving it a go. You'll learn what you know and what you don't know. And so go ahead and dive in. You know what to do. Okay, if you were able to complete the problem, congratulations. If not, you'll learn something and you'll win either way. Let's see how you did. I'm going to start by drawing a picture of this. And the picture of this, and again, you should think about the graphs of these things as you're doing it. This ends up being a limacon, and it has one of these little loops in it. Now, some students might think that this is just a figment of some mathematician's imagination, but actually there are applications in this. Limacons arise in the study of planetary motion. In particular, the trajectory of Mars, as viewed from the planet Earth, has been modeled by a limacon with a loop, as kind of shown here. Now, I am going to tell you that another phrase for this in the literature is retrograde motion, but sometimes it looks like you're going forward and then it looks like you're going backwards for a while, then you go forwards again. That's what this is looking like from the Earth. So anyway, I showed you a graph of that. That's the red. And there is a point here too that we're going to need to draw the line, and so I want to remind you of what happens with that. The only thing we really know, we know that r is equal to 3 plus 8 sine theta, and we know that we're looking at where theta equal pi over 6. So if I put pi over 6 in here, what I get for this is going to be 1/2, and 8 times a half is 4, and 3 and 4 is 7. So r is 7. So that means I actually have a little right triangle going on here, that r is 7, but theta is the angle. I could have made a theta there, but it wasn't worth my time, so I just typed theta, but you have theta there. But we know that this is a 90, 30, 60 right triangle, pi over 6, pi over 3, and pi over 2. So I know this is a special triangle with the size ratio of 1, 2, and the square root of 3. And so that tells me that this side here, which is the y coordinate, is 7/2, and this side is 7/2 times the square root of 3, and I just wrote it as root 3 because I did, I guess. Okay, so this is how I got this point, and notice that I dotted it in blue here. So we want to find the tangent line that goes through that point. That's what we're trying to do in this problem, and that's what the geometry looks like. All right, let's look at the solution now. And you see, here's the equation that we're going to be using. This was the one that we derived earlier. And so we need dr d theta. So we're going to say, what is dr d theta? Well, up here is r, so dr d theta is going to be the derivative of 3 is 0. This is 8 cosine theta. So I have that. So I just plug that into my formula. So I put 8 cosine theta times sine theta plus r. This is what r is, times cosine theta. That's my numerator. My denominator is going to be dr d theta, which is 8 cosine theta, times cosine theta yet again. So that is 8 cosine squared theta minus, and then this is r again, times sine theta. And so the r is, here is r. There's the sine theta. And then I really should simplify this so I can plug numbers into it. And I simplify this, and you should follow the algebra, but I get 16 cosine theta sine theta plus 3 cosine theta, all divided by 8 cosine squared theta minus 3 sine theta minus 8 sine squared theta. And there are some fancy things you could do with cosine squared theta, sine squared theta, but you don't have to. You're really just plugging in numbers, and the theta that you're plugging in is pi over 6, which is a special triangle. So you should be able to do this actually without calculators, but I do it. So I plug it in here. Make sure you follow this. But when I do that calculation in the numerator, I'm going to get 4 square root of 3 plus 3 root 3 over 2. In the denominator, I'm going to get 4 minus 3 over 2. And when I do simplification of that, I get 11 square root of 3 over 5. And that means that's the slope of my line because this is dy dx. So you see, previously I found out that the x coordinate was this one. the y coordinate was this one, and now I know the slope, so it is y minus, I could have said y minus the y coordinate, but I put this on this side is equal to the slope times x minus the x coordinate, and so I substitute that in, and that is the tangent line. And it's not quite in the slope-intercept form yet, but I think I'm going to stop there. And now I will just check my work. So I will graph it. Now, it turns out that none of the technology is important, and this was blue when I graphed it, but then I overrid it with green, and so it made it into green. But you see, yes, I have found this tangent line, and that's what it is. Now, some of my students will say, Jim, that's the ugliest damn line I've ever seen in my life. Well, I tell them there are no ugly lines, just like there are no ugly numbers, just like there are no ugly babies. And I have asked problems like this on assessments before, so please pay a lot of attention to this example. Let's do another one. So now we're talking about, this is going to be a cardioid, which we studied in the earlier section. So r is equal to 1 plus sine theta. I am not, I will show you a graph, but I would ask the question in this way. You want to find the slope of the tangent line when theta equal pi over 3. Now notice that I'm not asking you to find the whole equation, just the slope. I could ask you to find the whole thing. And then I ask you a little bit different question here. It is find the points on the cardioid where the tangent line is horizontal or vertical. You know what to do. Let's see how you did. And again, congratulations if you got it. If not, you learned something. Either way, you win. Okay, here is the graph of this cardioid, and you see it is a heart-shaped kind of beast, and you should be able to sketch a graph of that. Okay, now we're going to use our new formula for this derivative. I showed you it on the other page, and on a couple of other pages, so that's the formula we're using, and this is actually the whole formula that's right here. So I need to have dr d theta again. So if I take dr d theta, I'm going to get that dr d theta is cosine theta. So I get cosine theta times sine theta, plus this is r, and there was what r was, times cosine theta. So that's what is my numerator. My denominator, I take that derivative again, I get cosine. It's cosine times cosine, which is going to be cosine squared, and then here we have minus r, and that is sine theta. This was r, and so I substitute all that stuff in. And let's see, we were supposed to do that when theta is equal to pi over 3. A lot of times it's useful for you to do simplification, and you should be able to follow the algebra. Wow, and trig, I guess, that's done here. I guess I'm really going to call it algebra. But anyway, we're substituting theta equal pi over 3. Again, you should be able to do that without a calculator. So when we substitute those values in, this is dy dx then, and theta equal pi over 3. You substitute it in, you get an expression like this. It really is very useful for you to substitute, to simplify this, because this actually simplifies very nicely, and it is useful for you to follow the calculations. So this will simplify to this, will simplify to this, and now you see that the numerator is the negative of the denominator. That means the slope is minus 1. Now let's go back and see where is that on the graph, and it's right here. Now I didn't ask you to find the point, but if you found the point, this would be 1 plus root 3 over 2. And notice that this is not the same thing as 1/2 1 plus root 3. It's a different number. This is a different calculation, but it is there. And then this, so that is r, and this is theta, and theta is pi over 3. And the way you could do this is using r, and the x and y values are sine and cosine. So anyway, this is the place where it is minus 1. And all I ask you to do is find the slope of the tangent line. So the answer is minus 1, but I could have asked you to find that point as well. Now we're going on to part B. Part B says find the points. Now we're finding points, but now we're saying the tangent line is horizontal or vertical. Now, if the tangent line is horizontal, that means it is 0. And that means that in this case, dy d theta is equal to 0. Or vertical, that means that dx d theta is equal to 0. And if that's not ringing true, think about it and go back to the chapter with parametric equations. Okay, so here we go then with calculation. Oh, and here's our cardioid. That's the same one we drew before. But you see, now we're trying to find this point, this point. Those are the vertical tangents, and also the horizontal tangents. So there is a horizontal tangent that's 0. There's a horizontal tangent that's 0. There's a horizontal tangent that is 0. Okay, so let's see. We're going to have 2 answers for the verticals, and we're going to have 1, 2, 3 for the horizontals. Okay, here we go. So observe that dy d theta is this. Now I'm just taking the derivative of dy d theta. And again, I had what y was before, so I'm going to set this equal to 0, and I have to solve this. So this is going to be 0 when this one is 0 or when this one is 0. Now the cosine of theta is going to be 0 at pi over 2 and 3 pi over 2, and this other one is going to be 0 when sine of theta is minus 1/2, so that is going to be 7 pi over 6 or 11 pi over 6. So you see that gives me my vertical tangents, but we have to stay away from places where this one is 0. You have to go back and look at this, but then dx d theta is going to be 1 plus sine theta times 1 minus sine theta, and that's going to be 0 when these values happen. So when they're both 0, you can't do this. So we're not going to have, we're going to be rejecting this answer right here. So you see what we're going to get is 3 places, and again, that's 0 over 0, and that's undefined. Now what that really means is you're getting this cusp here, and you at 0, 0, and you see there is no tangent line there at all. Okay, so what I'm going to have is I'm going to have when theta is pi over 2, which will give me 2 pi over 2, and I'm also going to have these two values, which are going to give me these two values down here. I guess I should read instead of looking at the picture. Therefore, there are horizontal tangents at 2 pi over 2, 1/2, 7 pi over 6, 1/2, comma, 11 pi over 6, and vertical tangents at 3/2, comma, pi over 6, and 3/2, 5 pi over 6. Now, when theta is equal to 3 pi over 2, which is the one I just kind of casually crossed out, what really happens is we have to use L'Hopital's rule to calculate that. So the limit is going to be, here's the first step in L'Hopital's rule, and again we're going to be taking the derivatives, and so what we're going to get is this is going to be minus 1/3. That's what happens here, and then we get cosine of that's what this first limit is, but this one we have to use the this is going to be 0 over 0, and so I have to use L'Hopital's rule here. So there's the minus 1/3. I take the derivative of the top, getting minus sine theta, the derivative of the bottom, getting cosine theta. I plug that in. This is infinite. Now what that really tells you is that the derivative doesn't exist there, and you can see that that's the cusp in the graph. So this is equal to minus infinity. I forgot the minus sign there. And actually, oh, by symmetry, you know, coming from the other side, it's the same. So there's a vertical tangent at the pole, and the vertical tangent is this one as well, because it's minus infinity. Excuse me. So there's a vertical tangent there as well. So the vertical tangents then here, 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 3 vertical tangents, and there are 3 horizontal tangents. So it's 3 and 3. Now note, instead of trying to remember that fancy equation, you could just always think about, oh, x is equal to r cosine theta, and y is equal to r sine theta, and that helps you doing this instead of always remembering that formula. I don't know, that's pretty much up to you. Again, this is the general formula for parameters, and this is what it is when you're dealing just with theta as the parameter. And again, all of this relied on r being a function of theta. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. We're in this together. May God bless you all.